Something out past Neptune is pulling on the solar system. It hides from every telescope we own. We only see what it does. Frozen worlds billions of miles away swing in orbits that all lean the same way, like iron filings near a buried magnet. Tonight we hunt it. A world that takes 20,000 years to circle the sun. A rock called ammonite that breaks the pattern. A black hole the size of a bowling ball. If this grips you, hit like and subscribe now. Into the dark. Before anyone pointed a telescope at Neptune, a man sitting at a desk in Paris already knew it was there. He had no photos. He had no special equipment. He had a quill, paper, and a complete belief that the universe obeyed rules. The year was 1846. Astronomers had been tracking Uranus for decades, and something kept tugging it off course. Every calculation said Uranus should be in one place. The actual planet showed up somewhere slightly different every single time, and that gap between prediction and reality was small but stubborn. Year after year, the gap refused to go away. Urbain Le Verrier was a French mathematician who believed the universe followed rules, strict rules. So if a planet kept defying the math, something else had to be pushing it. He sat down with nothing but numbers and gravity equations, and he worked backward. If there's an unknown mass out there pulling on Uranus, where would it have to be? He sent his answer in a letter to an astronomer in Berlin. The letter arrived on September 23rd. That same night, the Berlin astronomer pointed his telescope at the exact coordinates Le Verrier sent. Within an hour, he had found Neptune, less than 1 degree from where the math said it would be, a planet discovered by pure thought. That moment changed science forever. It proved something remarkable. You don't always need to see something to know it's real. If the universe is following its own rules, and something is breaking those rules, then something else must be hiding out there causing the break. Keep that idea in your head, because nearly 200 years later, astronomers found themselves staring at the same kind of problem. A whole group of frozen worlds at the edge of our solar system were moving wrong. Their orbits were tilting, clustering, and pointing in directions that made no sense on their own. The math kept pointing at a gap, and in that gap, something had to be sitting. Le Verrier's method is exactly what modern astronomers use to predict where a hidden ninth planet might be lurking right now. The logic is identical, the evidence is stranger, and the scale is almost beyond imagining. Neptune is roughly 2.8 billion miles from the Sun. The hidden world we're chasing sits somewhere between 40 and 80 billion miles away from us. So far, that even the fastest spacecraft we ever built, traveling at 35,000 miles per hour, would take 160 years just to reach it. And yet, the same trick that found Neptune in a single evening might find this too. There is something almost eerie about that parallel. The same logical structure, the same gravitational reasoning, now applied to a scale Le Verrier could never have imagined. He found a planet 30 times farther from the Sun than Earth. We are hunting one that may be 600 times farther. But before we get to the hidden planet, we need to understand the man who accidentally ripped open this mystery while trying to find something else entirely. A stubborn, obsessive astronomer who spent the last years of his life hunting a ghost, built his own private observatory in the Arizona desert, and died before he ever got an answer. His name was Percival Lowell, and the planet he was chasing was never what he thought it was. Percival Lowell was rich, stubborn, and absolutely certain a hidden planet was out there. He had already made himself famous by claiming Mars was covered in canals built by a dying civilization. The scientific community mostly laughed at him, so he turned his attention to something he believed would redeem his legacy. A massive, undiscovered world lurking beyond Neptune that he called Planet X. The X stood for unknown. In 1905, Lowell started a systematic search from his private observatory in Flagstaff, Arizona. He hired teams of people to photograph the sky night after night, staring at thousands of glass plates, looking for a dot that moved. Stars stay still between photos. A planet crawls. He searched for 11 years. He found nothing. Then, in 1916, Lowell died of a stroke. His telescope kept going. His staff kept photographing. And 13 years after his death, in 1929, a 22-year-old farmhand from Kansas named Clyde Tombaugh took the job nobody else wanted: blink comparator operator. The blink comparator was a machine that flicked between two photos of the same patch of sky taken on different nights. Tombaugh stared through the eyepiece for hours at a time, watching thousands of stars, looking for anything that shifted position. One dot that hopped even slightly between images could be a planet. On February 18th, 1930, after less than a year on the job, Tombaugh found one. He reportedly sat quietly for 45 minutes before telling anyone. He had a habit of confirming things twice before speaking. The dot was real. It moved, and it sat right where Lowell's math had predicted Planet X would be. The discovery exploded across the world. Schools let children out early. Churches rang their bells. A planet had been found. An 11-year-old girl in Oxford, England, named Venetia Burney suggested the name Pluto after the god of the underworld. The name stuck the same day she said it. But here is where the story quietly falls apart. Pluto was tiny, smaller than our moon, far too small to produce the gravitational tug that was supposedly pulling Uranus off course. Lowell's Planet X was predicted to be enormous, several times the mass of Earth. Pluto had nowhere near enough gravity to do the job. Scientists eventually realized something else. The supposed wobble in Uranus's orbit that started this whole search was an illusion. It came from small errors in the original measurements. Once astronomers got better data, the wobble disappeared. Planet X had been a ghost of bad math, so in a strange twist, Lowell spent his life and his fortune hunting the wrong planet for the wrong reason. And the planet his team found was real, but completely unrelated to his original theory. And decades later, when astronomers stripped Pluto of its planet status, in 2006, the solar system was left with 8 planets. The 9th chair sat empty. Something about that emptiness bothered people. And as telescopes got sharper and the outer solar system slowly came into focus, astronomers began to notice that the empty chair might have a new occupant, one that made the search for Pluto look simple, one that hides in a place where sunlight barely reaches and where a single year lasts longer than human civilization has existed. But before we go out there, we need to understand the neighborhood. On August 24th, 2006, 424 astronomers in Prague voted on a definition. Most of the world did not notice. Pluto did not survive it. The International Astronomical Union had been arguing for years about what exactly qualifies as a planet. The debate was not new, but in 2006, they finally drew a hard line. To count as a planet, a world has to meet 3 conditions. It has to orbit the sun, it has to be round from its own gravity, and it has to have cleared its neighborhood of other objects. Pluto orbits the sun. Check. It rounds itself into a sphere. Check. But Pluto shares its neighborhood with thousands of other icy bodies in the ring beyond Neptune. It has never dominated its orbital zone. So the vote passed. Pluto became a dwarf planet, and the solar system shrank to 8. People took it personally. School children wrote letters of protest. Scientists who had grown up with 9 planets felt something get quietly removed from the mental map of where we live. Mike Brown, the Caltech astronomer who had discovered a body even larger than Pluto called Eris, later said he felt like he killed Pluto. He did not mean it as a boast. He seemed genuinely conflicted. The demotion felt personal to millions of people who had grown up counting 9 planets on their fingers. The media covered the vote. Schools updated their posters. Textbooks started shipping new editions. And a generation of students spent the next few years arguing about it at lunch. But here is what almost nobody talked about in 2006. Eris was the trigger. When Brown's team found Eris in 2005 and measured it as slightly larger than Pluto, the argument about Pluto's status became unavoidable. If Pluto was a planet, then Eris was a planet. And Eris was in a wild, tilted orbit far outside the normal flat plane where the 8 planets circle. If they kept Pluto and Eris, the solar system would soon have dozens of planets, so they drew the new rule. And the same Mike Brown who triggered the demotion walked out of that conference thinking about something nobody else was thinking about yet. Out past Pluto, out past Eris, out past the ring of icy rubble that surrounds the outer solar system, the math was still behaving strangely. Some of the most distant objects known were moving in ways that the 8 planets alone could not explain. The 9th chair was empty by vote, but the evidence for something sitting in it was quietly building. Most people went home from Prague and moved on. Brown did not. He started looking at the data from a different angle. He had spent years cataloguing the outer solar system. He knew where everything was. And more, the things he was finding in the deep dark were arranged in a pattern that had no obvious cause. The outer solar system had a shape, and something had to be shaping it. Brown was not alone in that feeling. Scott Shepard at the Carnegie Institution for Science had been hunting distant objects too. Chad Trujillo at Northern Arizona University was doing the same. Separately, across different teams with different telescopes, a quiet unease was building. The outer solar system kept showing patterns that the 8 planets alone could not produce, a shape that required a sculptor. What was that ring beyond Neptune, exactly? What lived out there? Because before you can understand what is bending it, you need to understand what it is. It is stranger and more crowded than most people imagine. Most people picture the solar system as 8 planets moving in neat circles around the sun, with empty space beyond Neptune. Clean, orderly, done. The Kuiper Belt broke that picture, starting just beyond Neptune and stretching out to about 50 times the Earth-Sun distance. The Kuiper Belt is a massive ring of frozen debris, billions of objects, chunks of ice, rock, and frozen gas left over from the earliest days of the solar system, preserved at temperatures around 370 degrees below 0 Fahrenheit. And it is enormous. If you could drive across the Kuiper Belt at highway speed, the trip would take several billion years. Pluto lives here. So does Eris. So do thousands of other frozen worlds we have only recently begun to catalogue. Some are a few miles across. Some are hundreds of miles wide. The belt is so thick with objects that early solar system scientists never imagined it could exist. For decades after Pluto's discovery, astronomers assumed the outer solar system was mostly empty. Gerard Kuiper, the astronomer whose name the belt now carries, actually argued there should be no belt at all. He thought the outer solar system had been swept clean long ago by Pluto's gravity. He was wrong, and his name ended up on the thing he said could not exist. The first confirmed Kuiper Belt object beyond Pluto was found in 1992. Within a few years, dozens more appeared, then hundreds. The outer solar system was overflowing. Astronomers had been looking at a tiny slice of it and assuming they were seeing the whole picture. The true scale was humbling, but the Kuiper Belt does something unexpected. It ends around 50 times the Earth-Sun distance. The number of objects drops sharply. Astronomers expected the belt to taper off slowly, like the edge of a city fading into countryside. Instead, it stops like a wall. The density falls by a factor of 100 in a very short stretch of space. They call it the Kuiper Cliff. Nobody has a fully satisfying explanation for why it is there. Some models of how the solar system formed predict there should be far more material out beyond that edge. The current leading idea is that something swept the region clean long ago. Maybe an unseen planet. Maybe Neptune, migrating outward and pushing material in front of it like a plow. But here is the part that really pulls at astronomers. Out past the cliff, in the near-empty space beyond, some objects do exist, and their orbits make the Kuiper Cliff look like a footnote. These objects are so far out, and their paths so extreme, that nothing in our current map of the solar system could have put them there. They move in long oval orbits that swing out to distances almost impossible to visualize. They get close to the sun maybe once in every few thousand years, spend most of their time in the dark, and then crawl back toward us before swinging out again. The first one found had a name that sounded almost mythological, and its discovery sent a quiet shock through the field that built slowly into something much louder. It was found in 2003, and it was the object that, years later, helped crack open the entire Planet 9 mystery. The Kuiper Belt should fade. Every model of how planets form, every computer simulation of the solar system's early life, predicted the same thing. As you move outward from the sun, the density of material should drop off gradually. Like a song getting quieter, it drops off like a cliff. At around 50 times the Earth-Sun distance, objects in the Kuiper Belt go from common to nearly absent in a surprisingly narrow band of space. Astronomers call it the Kuiper Cliff. It is one of the most puzzling structural features in our entire solar system, and after 30 years of study, no one fully agrees on what caused it. The numbers tell the story. Inside the cliff, the belt contains thousands of known objects. Astronomers expect there are hundreds of thousands more too faint to spot yet. Move past the cliff, and the count collapses. The population shrinks by a factor of roughly 100. Space does not usually behave like that. Gradual transitions are normal. Sudden walls are not. Several explanations have been put forward. The one with the most support involves Neptune. Early in the solar system's history, Neptune migrated outward from its original orbit. As it moved, its gravity would have swept material ahead of it, like a plow pushing snow. The material piled up inside what is now the main Kuiper Belt, and the region beyond got stripped. That's why the cliff is where it is. But that explanation does not close every gap. Some models predict that even after Neptune's migration, enough material should have survived past the cliff to keep the population relatively dense. The actual cliff is sharper than those models produce. Something may have also worked from the outside, clearing the region beyond the edge. A planet would do the job perfectly. A world large enough to dominate that distant region would gravitationally sculpt the area over billions of years. Its presence would explain both the sharp outer edge of the belt and some of the stranger orbital behaviors observed in objects that do survive out beyond it. Astronomer Renu Malhotra put it clearly when she described the warp she and her colleagues kept finding in the outer solar system's orbital architecture. The amount of the warp, she said, felt crazy. That word crazy in the mouth of an astronomer describing observed data carries weight, because the Kuiper Cliff is just the beginning of the strangeness. A sharp outer edge on a ring of debris is puzzling. What lives beyond that edge is in a different category entirely. Objects found out there do not behave like anything Neptune or the known planets could explain. Their paths are too long, too tilted, and too extreme. The first of those objects had a discovery story attached to it that stopped astronomers in their tracks. Not because of what it was, but because of where it was and what its presence meant. It was 2003 when Mike Brown's team found it. They were sweeping the outer solar system looking for large Kuiper Belt objects, the kind that might deserve the title of dwarf planet. They found something that fit no category anyone had prepared for. A red, frozen world on a path so far out that no known force in our solar system could have put it there. And when they looked at the orbit more carefully, things got strange fast. Mike Brown did not set out to upend solar system science. He was cataloging, systematically sweeping the sky with a wide-field camera, photographing patches of sky, then coming back to the same patches and comparing images to find anything that had moved. That was the job. In November 2003, a dot moved. His team confirmed it over several nights. The dot was real, it was distant, and it was enormous. It had a reddish color, unusual for outer solar system objects. And when they calculated its orbit, Brown felt something shift in his understanding of the solar system. The object, given the formal name Sedna, after the Inuit goddess of the sea, had a closest approach to the Sun of about 76 times the Earth-Sun distance. That put it well outside Neptune's gravitational reach. But the truly startling number was its farthest point, Sedna swings out to roughly 937 times the Earth-Sun distance before looping back. Its full orbit takes about 11,400 years. Let that picture form. Sedna has been circling the Sun since before humans built the first cities, and in that entire time, it has not completed even one full lap. Every major civilization in history has risen and fallen, while Sedna barely moved a fraction of the way around its path. And here is the problem. Sedna's orbit makes no sense. For an object to end up in that kind of path, it needs a gravitational nudge. Something had to push or pull it into that extreme oval orbit. Nearby planets can toss objects outward, but only to certain distances. Neptune can pull on things out to maybe 30 times the Earth-Sun distance with any real strength. Beyond that, its grip fades. Sedna is far beyond Neptune's reach at its closest point. The Oort cloud, the vast sphere of icy debris thought to surround the outer solar system at enormous distances, can sometimes have its members pulled inward by passing stars. But those objects come in from distances of thousands of times the Earth-Sun distance. Sedna is not far enough out to be an Oort cloud object. Sedna sits in a gap, too far for the planets to have put it there, too close for passing stars to be the main culprit. When Brown looked at that orbit, he wrote in his research journal that it felt like finding a city in the middle of the ocean. Cities have to be built by something. Objects in impossible orbits have to be put there by something. Some astronomers proposed that early in the solar system's history, when the Sun was still forming inside a dense cluster of other young stars, a close stellar neighbor could have gravitationally disturbed the outer solar system and scattered objects like Sedna into these extreme paths. Those companion stars eventually dispersed as the cluster broke apart, but the disturbed orbits they caused remain billions of years later, as fossils of a time we can barely imagine. Fossils. That word would come back years later with a new discovery that complicated everything. For the moment, Sedna was treated as a strange exception, maybe a one-off, maybe a curiosity. Brown moved on and kept cataloguing. Then more of them started showing up, and they were all doing the same strange thing. When astronomers found Sedna, they ran the numbers and came up against a wall. The closest Sedna ever gets to the Sun is still so far out that our star, from Sedna's surface, looks like a bright dot you could cover with the head of a pin. It delivers almost no warmth. It exerts almost no tidal force. And yet Sedna is clearly in a stable orbit around it. The question of why that orbit exists is where things get uncomfortable. For an object to end up in an elongated oval path, something has to have disturbed it from a more circular starting point. The universe does not hand out extreme oval orbits for free. You need a gravitational event, a close pass from a large mass, a significant tug at the right moment. Our solar system's planets can do this. Jupiter has been throwing objects around for billions of years. Neptune, as it migrated outward early in solar system history, scattered chunks of debris all over the outer solar system. But those processes have limits. Neptune's ability to significantly alter an object's orbit drops off sharply past a certain distance. That distance is well inside Sedna's closest approach to the Sunday. In simple terms, Sedna starts its closest approach at a point where Neptune barely tugs on it at all. Neptune could not have put it there. And passing stars? That theory works, but only under specific conditions. To scatter an object into Sedna's kind of orbit, a star would have to have passed fairly close to our Sun, within a few hundred times the Earth-Sun distance. Stars do pass by. They just take millions of years, and there is no record of a close enough encounter that could explain Sedna alone, unless it happened very early, when the Sun was still in its birth cluster of stars. That idea is compelling. Young stars are born in groups called stellar nurseries. Our Sun probably formed surrounded by hundreds of sibling stars. Over millions of years, that nursery dispersed. But before the siblings drifted away, their gravity could have stirred the outer edges of our forming solar system, flinging objects like Sedna into those extreme orbits. A memory of a time the Sun was not alone. Brown described the discovery of Sedna as one of the strangest moments in his career, an object that existed in a place that the known solar system could not explain. He compared it to finding a bear swimming in the middle of the Pacific Ocean. The bear is real. The Pacific is not where bears live. Something happened. The birth cluster idea is compelling but hard to test. We cannot go back 4.5 billion years and photograph the sun's siblings. We can only look at the orbits left behind and ask what force would have been needed to create them. The answer keeps pointing to something large, something close, and something no longer there, or at least, something no longer close. At the time, the scientific community treated Sedna as an anomaly, an interesting outlier that required more data before anyone should draw large conclusions. Brown agreed with that caution. He kept looking, and a decade later, another team found something that turned a single strange bear in the Pacific into a whole parade of them. The parade was all going the same direction, and that direction made no sense unless something massive was standing at the end of it. In 2014, Chad Trujillo and Scott Shepard published a paper that got the scientific community's attention. Trujillo had worked with Brown years earlier when they found Sedna together. Shepard was a veteran planet hunter at the Carnegie Institution for Science. They had spent years cataloging the most distant objects in the solar system, and they had built up a collection of 13 extreme trans-Neptunian objects, meaning frozen bodies orbiting the Sun far beyond Neptune's reach. When they mapped the orbits of all 13, they noticed something that made them stop. Every single one of them shared a specific orbital feature. The point in each orbit where the object swings closest to the Sun was clustered in the same direction in space. Astronomers call that the orbital perihelion. Across 13 completely different objects, on 13 completely different paths, the pericenter clustered. They all pointed their closest approach end toward the same general region of the sky. Random orbits do not do that. If these objects were just random debris scattered over billions of years with no single outside influence, their pericenter directions should be spread all over the place, evenly distributed across the sky like points on a compass pointing every direction equally. Clustering like this had a probability of less than 1 in 100 of happening by chance. Something was herding them. The image that fits is a sheepdog and a flock. A good sheepdog can steer a herd in a specific direction without the sheep understanding why they are all going the same way. A massive, unseen planet far out in the outer solar system could act as a gravitational sheepdog, nudging these objects over millions of years until their orbits all leaned the same direction. Trujillo and Shepard were careful. They proposed that a distant, massive body could explain the clustering, but they stopped short of claiming a planet was definitely there. They called for more observations. More objects needed to be found and measured before a confident conclusion was possible. What they had was a signal, and the signal was real. Brown picked up the paper and read it carefully. He felt something he had not experienced since the morning he found Sedna, that restless, unsettling sense that the map of the solar system was wrong. He brought it to his colleague, Konstantin Batygin. Batygin was younger, with a physicist's instinct for theory and a talent for building simulations. Brown had the observation history and the inner solar system experience. Together, they decided to attack the problem head-on. They ran simulations. They built a virtual solar system. They tried to explain the clustering with known forces. Nothing worked. No combination of the 8 known planets produced an orbital pattern that matched what Trujillo and Shepard had found. Then they tried something different. They added a 9th planet, and the solar system in their simulation, for the first time, started behaving like the real one. But the planet they needed to make the simulation work had properties that made some scientists uncomfortable. It had to be massive, it had to be far away, and it had to be moving in an orbit that seemed almost designed to avoid every telescope humanity had ever built. What exactly did their planet look like? And why did it produce something even stranger than the clustering they started with? Konstantin Batygin was skeptical from the start. When Brown brought him the clustering data, Batygin's first instinct was that it was an artifact, something wrong with the observations. A bias in where telescopes pointed, because telescopes do not cover the sky evenly. They observe more where conditions are best, and that uneven coverage can create patterns that look real but are not. So, they tested for that first. They analyzed whether the clustering could be explained by observational bias alone. They ran those numbers carefully. It could not. The clustering was real, and Batygin moved from skeptic to hunter. They spent over a year building computer simulations of the outer solar system. Their approach was mathematical and physical, given the orbital properties of the 6 most extreme distant objects then known. What mass and orbit would an additional body need in order to cause this clustering pattern to appear? The simulations converged. The answer that fit best was a planet roughly 10 times the mass of Earth, orbiting the Sun in a highly elongated path. Its closest approach to the Sun would be somewhere around 200 times the Earth-Sun distance. Its farthest point would be somewhere around 600 to 1200 times the Earth-Sun distance. To compare, Neptune, the farthest known planet, orbits at about 30 times the Earth-Sun distance. The hidden planet Batygin and Brown were predicting sits somewhere between 6 and 40 times farther out than Neptune. The Sun, from the surface of this predicted world, would look like the brightest star in the sky, bright enough to read by, in theory. But the temperature on its surface would be somewhere around minus 370 degrees Fahrenheit, cold enough that any atmosphere it might have would be frozen solid onto the ground. But here is where Batygin made an unexpected finding inside the simulation. He was testing what the predicted planet would do to the 6 clustered objects when he noticed something the simulation produced that he had not asked for. Some objects came out of his simulation with orbits tilted at roughly 90 degrees from the main plane of the solar system, orbiting sideways, like a coin standing on edge relative to a tabletop. He brought those results to Brown. And Brown stopped, because those objects existed. 4 of them had already been found in the real outer solar system, orbiting at roughly 90 degrees to the main planetary plane, exactly as Batygin's simulation predicted. Brown had not told Batygin about them beforehand. The simulation produced them independently. That was a prediction confirmed by a discovery that had already been made. In science, that kind of backward confirmation carries serious weight. The planet in their simulation was not just explaining the clustering, it was explaining things they had not even asked it to explain. Their paper came out in January 2016, and then the world found out about Planet 9. The story hit every major news outlet. Astronomers who had never worked on the outer solar system started paying attention, and the debate that erupted was fierce, because not everyone agreed the evidence was solid. Some had a very different explanation for the clustering. We will get to that disagreement. First, we need to understand exactly what the clustering showed, because there was a second layer to it that Batygin found months later, one that stunned even him. Picture a bunch of clock hands all frozen at the same time. 12 different clocks in 12 different rooms. None of them connected. No one has touched them since they were set. You walk in, and every single one reads 3:15. The probability of that happening by chance is essentially 0. Something synced them. That is what Batygin and Brown found with the orbits of the most extreme distant objects in the solar system. The clustered objects they studied were each on their own independent paths around the Sunday. Some of those paths take thousands of years to complete. Some take tens of thousands. They were laid down by whatever gravitational events happened in the solar system's early history billions of years ago. There is no reason why they should show coordinated behavior in any direction. And yet, the ends of their orbits, the sides that point farthest from the Sun, all cluster together in the same region of the sky. From above, if you mapped these orbits like the spokes of a wheel, they bunch up on one side instead of spreading evenly. Batygin and Brown analyzed the statistics carefully. They calculated the probability that this clustering happened by chance, with no unseen massive body causing it. The result was roughly 1 in several hundred, depending on the exact sample of objects used. That means random chance is unlikely as the explanation. Something is causing the alignment, and the only force that works at those distances, that is powerful enough and operates over billions of years, is gravity from a large mass. The predicted planet sits roughly on the opposite side of the Sun from where the clustered objects bunch up. This makes sense physically. A massive body in that position would gravitationally shepherd the distant objects, nudging them over countless orbits until their trajectories all point away from the planet's general location. Think of it like a gravitational crowding effect. The planet pushes the distant debris into a configuration that clusters on the far side. But the clustering was only the first line of evidence. What Batygin found next was unplanned, and it hit him harder than the original result. After publishing the 2016 paper, he kept running the simulation. He wanted to understand more about what the predicted planet would do to the broader outer solar system population. And in those follow-up runs, the simulation kept spitting out objects with something very specific: orbits tilted far above and below the main planetary plane. Most planets orbit within a few degrees of the flat disk of the solar system. These simulated objects were popping out at 15, 20, even 25-degree tilts. They were genuinely warped relative to the rest of the solar system. When Batygin and Brown went looking in real observational data, they found those tilted objects too, 5 of them at extreme inclinations. Their tilts matched the simulation's predictions almost exactly. These were objects no one had predicted. The simulation produced them on its own, and they were already sitting there in the real solar system, waiting to be explained. Astronomer Renu Malhotra measured the warp in these orbits and called it crazy. That word carries weight when it comes from a scientist describing something real. But the strangest prediction from the model was yet to come, and it involved the Sun itself. Something is tilting the solar system's distant objects. Most things in the solar system orbit close to a flat disk called the ecliptic plane. The 8 major planets stick to it tightly, within a few degrees. When you see diagrams of the solar system, that disk is what everything circles in. It was inherited from the spinning cloud of gas and dust the solar system formed from. Flat disks are natural outcomes of rotating systems. So, finding objects whose orbits lean steeply off that disk is unusual. Finding a whole population of them, all tilted in the same direction by roughly the same amount, is something else entirely. When Batygin and Brown mapped the orbits of the distant extreme objects they had been studying, they found a consistent pattern in the tilt angle. Their perihelia clustered in one direction, as already described, but separately, their orbital planes were leaning off the main disk by an average of about 15 degrees, and that average lean had a direction. They were all tilted toward the same side of the solar system. This is not something the 8 known planets can produce. The combined gravitational influence of Jupiter, Saturn, Uranus, and Neptune does cause some tilting in outer solar system objects, but the effect falls off quickly with distance. Out where these extreme objects live, the known planets barely breathe on them. Planet 9, with its predicted orbit, would produce exactly this tilt pattern. Its gravity, operating over billions of years from its remote location, would gradually torque the orbits of objects it interacts with, twisting them off the main plane and pointing them in a specific direction. The tilt becomes a gravitational fingerprint. Think of it this way. Imagine spinning a basketball and then pressing your palm gently against the side of it at an angle. The ball's spin axis shifts slightly. Planet 9 is the palm. The distant frozen objects are the basketball's spin. Over billions of years, the planet's gravity has been pressing those orbits off axis. That picture held up across multiple independent teams who analyzed the data. The tilt was real, the direction of the tilt was consistent, and the known solar system had no ready explanation for it. But the tilt in the distant objects turned out to be only half the story. Because there was something strange about the Sun itself. The Sun does not spin on the same axis as the plane of the solar system. Every planet orbits roughly in the same flat disk, and the Sun spins, but the Sun's spin axis is tilted about 6 degrees from perpendicular to that disk. 6 degrees sounds small, Over nearly 5 billion years of formation and gravitational settling, the Sun should be spinning exactly in line with the planetary disk. Everything that formed from the same cloud should share the same spin orientation. That 6-degree lean has puzzled physicists for decades. Several explanations have been proposed, none of them satisfying until Batygin and Brown ran the numbers on what Planet 9 would do. A massive planet in a tilted, elongated orbit far out in the solar system would, over billions of years, pull on the entire planetary plane with a very slow, very gentle gravitational torque. That torque could tilt the planet's orbital disk relative to the Sun's spin axis by exactly the amount we observe, 6 degrees. Planet 9 could be the thing that tipped the Sunday. Some things in the outer solar system are orbiting sideways, completely sideways, while the 8 major planets and most known solar system bodies move in roughly the same flat disk. There exists a population of objects whose orbits are tilted nearly 90 degrees from that plane. They orbit like a coin balanced on its rim at the equator, while everyone else rolls flat along the floor. These objects are real. Astronomers have found several of them, and for years, no one had a convincing explanation for why they existed or how they got there. The classic formation story for solar system objects runs like this. Everything started in a flat spinning disk of gas and dust around the young Sunday. Gravity pulled material together into clumps. Clumps grew into rocks. Rocks grew into planets. The whole disk was flat from the start, so everything that formed from it ended up orbiting in roughly the same plane. Tilts build up slowly from gravitational interactions between planets, but those interactions cannot tilt anything by 90 degrees. That kind of extreme tilt requires an extreme cause. When Batygin was running his Planet 9 simulations in 2016, something unexpected kept appearing. His simulation kept producing objects with 90-degree tilts. These were not objects he programmed in or asked the simulation to create. They emerged from the physics. When a massive 9th planet with a tilted, elongated orbit gravitationally interacted with distant solar system debris over billions of years, some of that debris got driven into these extreme perpendicular paths. The process works through a mechanism called the Kozai-Ledoff effect. A massive body in a tilted orbit can pump up the inclination of smaller objects over time, eventually tilting them all the way to 90 degrees if the conditions are right. Imagine gently pushing a swing higher and higher over thousands of swings. Each push adds a little more height. Planet 9's gravity was the push. The perpendicular orbits were the result of a very long swing. Batygin published this prediction. 5 objects in the outer solar system were already known to have these high-inclination perpendicular orbits. When the simulation's results were compared to the actual positions and orientations of those 5 objects, they matched. Let that settle for a moment. The simulation predicted a population of objects that should exist with specific orbital properties before any search for them was conducted. The objects were already sitting there in the data, confirming the prediction. This is how Neptune's discovery worked. Math predicted where the planet would be. A telescope looked at that location and found it. Planet 9's situation is the same structure. Predictions first, confirmations after. The perpendicular objects were a confirmation that nobody went looking for. They were already catalogued, waiting for a model that could explain them. Batygin has called the perpendicular objects one of the most satisfying parts of the whole body of evidence. The simulation produced them without being asked to. No one set up the model to generate perpendicular orbits specifically. They fell out of the physics on their own, and the real solar system had already put them there. But there are still deeper fingerprints, because Planet 9 does not only tilt things sideways, it also causes a slow, rhythmic rocking motion in some objects' orbits, a gravitational heartbeat, and when Brown spotted it in the real data, it shook him. The Sun sits slightly crooked. This has been measured. The Sun's equator, the line along which it spins, is tilted roughly 6 degrees relative to the flat plane in which all 8 planets orbit. 6 degrees is small, But in a solar system that formed from a single spinning disk of gas and dust, everything should share the same axis of rotation. The planet's orbital plane and the Sun's spin plane should be nearly identical. They are not, and astronomers have been trying to explain the discrepancy for a long time. Some proposals involve the early solar system, before the planets finished forming. Maybe the disk of gas and dust was itself slightly warped. Maybe a passing star disturbed it during formation. These are plausible ideas in principle. They are also difficult to test, because whatever happened, it happened about 4.5 billion years ago. When Batygin and Brown finished their Planet 9 model, they asked a natural question. What would this planet do to the Sun's spin axis over billions of years? The planet in their model has a tilted, elongated orbit. It circles the Sun at a steep angle compared to the planetary disk. Over billions of years, that tilted orbital path exerts a very slow gravitational torque on the rest of the solar system. The force is tiny, but time amplifies everything. 4.5 billion years of tiny pushes add up. Their calculation produced a tilt angle close to 6 degrees. The number matched the observed offset in the Sun's spin axis. This result raised eyebrows inside and outside the field. A single object, too far away to see, on an orbit tilted from the planetary plane, could explain why the Sun has been sitting slightly crooked for billions of years. The Sun's lean is a gravitational echo of a world we have never directly detected. Planet 9 would not need to be visible to leave its mark on the Sunday. Gravity reaches everywhere, quietly and persistently. And 4.5 billion years is a very long time to accumulate a lean. The gravitational fingerprints were now stacking up. Clustered orbits, tilted paths, perpendicular worlds, the Sun's 6-degree offset. Each of these, on its own, might be explainable by other means. Together, they point at the same location. Consider what that means. An object we have never photographed, never measured directly, never confirmed even exists, has nonetheless left its signature on 4 separate, unconnected features of the solar system. Its gravity worked silently for billions of years, nudging, tilting, herding, and the results are written in the shapes of orbits across billions of miles. The Sun itself carries the mark, the most massive object in the solar system, responsible for 99% of all the matter in this neighborhood, tilted 6 degrees off its own axis. And that lean has a plausible explanation only if something very massive is pulling on the planetary disk from a steep angle outside. But some astronomers pushed back hard. The sample sizes were small, the observations were not evenly spread across the sky, and there was a troubling possibility that the pattern was not real at all, just an illusion produced by the limits of where we look. We will get to that challenge, because it is serious and deserves a full answer. First, there was one more fingerprint, and this one was the strangest yet, a rhythm. A slow gravitational heartbeat buried in the orbits of objects that nobody had thought to look at before. Brown was not looking for a rhythm. He was looking at data from objects whose orbits dip close to Neptune's path before swinging far out again, kind of like a comet diving toward the Sun and then arcing back out to the cold dark. These objects, called centaurs, live between Jupiter and Neptune and have unstable, evolving orbits. He was trying to understand where centaurs come from. The standard answer is the Kuiper Belt, where Neptune occasionally gravitationally deflects an object inward. Brown ran simulations of that process and kept finding something the model predicted that the real data also showed. The distribution of how closely these inward drifting objects approached the Sun was not random. There was a gradual, smooth drop-off in their numbers as perihelion distance decreased. In simple terms, there were far fewer objects getting very close to Neptune's orbit than the standard formation models predicted. Standard models said the population should fall off sharply right at Neptune's orbital distance. The real data showed a smooth decline that started farther out. Planet 9 explained that smooth decline. In Brown's simulations, when he included Planet 9, the distant planet's gravity was slowly feeding objects from the extreme outer solar system into the closer inner population. The feeding process was gradual and continuous, and the rate of that feeding matched the smooth distribution seen in the real Centaur population. This was a fourth independent line of evidence: clustering, tilts, perpendicular orbits. And now this, the pattern in Centaur populations that Planet 9's gravity naturally reproduces. Brown described the Centaur result as the line of evidence that finally removed his remaining personal doubt. He had tried for years to stay skeptical. He had tested alternative explanations for each piece of evidence one by one. But the Centaur distribution, he later said, was where he stopped being cautious and started being certain. He still had no telescope image of the planet, still no direct detection, but he had 4 independent phenomena, each one explained naturally by Planet 9, each one difficult or impossible to explain without it. None of those 4 phenomena were hand-chosen to fit the theory. The perpendicular orbits appeared unexpectedly in the simulation before anyone searched for them in real data. The Centaur distribution was a known puzzle before Planet 9 was proposed and turned out to fit the model afterward. The evidence was building from multiple directions at once: 4 lines, clustering, tilts, perpendicular objects, Centaur distributions, each from a different corner of the solar system, each pointing to the same unseen mass in the same general region of space. In science, when 4 independent experiments all give you the same answer, that answer is worth taking seriously. Brown said publicly that he would be genuinely shocked if Planet 9 turned out not to exist. He spent years trying to be skeptical. The data kept winning the argument. And then the story got its most important piece of new hardware: a telescope on top of a mountain in Chile, the largest camera ever built for astronomy, a machine that photographs the entire southern sky every few nights for 10 straight years. If Planet 9 is out there, this telescope has a strong chance of finding it. But there was still one enormous question nobody had answered. What exactly is this planet? Where did it come from? And could it possibly be something other than a planet entirely? The Centaur population was supposed to be simple. Centaurs are solar system objects with unstable orbits between Jupiter and Neptune. They do not stay in those orbits forever. Jupiter's enormous gravity nudges them inward and outward. Over millions of years, they get scattered away. The scientific understanding was that they come from the Kuiper Belt, where Neptune occasionally kicks an object onto an inward path, and the object then migrates inward and joins the Centaur population. It was a tidy picture, a known source, a known pathway, a predictable distribution. The distribution was wrong. When Brown analyzed how the Centaurs were spread across different orbital distances, he found a smooth, gradual population instead of the sharp cutoff the standard model predicted. Objects were leaking inward from farther out than Neptune's influence alone could explain. Something was feeding the Centaur population from the deep outer solar system. Planet 9 sits in that deep outer region. Its gravity, reaching inward over billions of years, slowly pulls on objects from the extreme outer solar system. Some of those objects gradually drift into orbits that take them closer to the Sunday. Over millions of years, they migrate inward until they enter the Centaur zone. The process is slow and constant, like water seeping through a crack in a dam. When Brown ran simulations that included Planet 9, the smooth, gradual Centaur distribution appeared naturally. The simulation matched the real data. The Centaur result matters for a specific reason. Every other line of evidence for Planet 9 involves objects in the extreme outer solar system, beyond Neptune and deep into the Kuiper Belt. Those objects are faint, few, and hard to observe. The sample sizes are small. Centaurs are relatively close to us, easier to observe, better catalogued. There are hundreds of known Centaurs, giving a much larger statistical base. When a large population of well-observed objects shows a pattern that Planet 9 naturally explains, the statistical power behind that evidence is considerably stronger. And the Centaur evidence is independent. It does not rely on the clustering of extreme distant objects. It does not rely on orbital tilts. It is a completely separate phenomenon, coming from a completely different part of the solar system, pointing at the same conclusion. This is how science builds confidence. Independent lines of evidence from different sources, all pointing in the same direction. Clustering, tilts, perpendicular orbits, Centaur distributions. And now one more pattern hiding in a population of objects that were never even part of the original Planet 9 discussion. The case was built from the edges inward. Every time a new piece of the outer solar system was examined carefully, Planet 9's predicted gravitational footprint appeared, sometimes in places nobody expected to look. But the question that followed naturally from all of this evidence was, what kind of object could do all this? What are we actually looking for out there? Something far colder than any world you have ever imagined. Something sitting in near complete darkness. Something so far away that even if you knew exactly where to look, most of our telescopes could not see it. A world 10 times the mass of Earth, orbiting the Sun at a distance so extreme that sunlight is barely a whisper there, on a path so elongated that it spends most of its time in the deepest cold imaginable. The physical description of Planet 9, if it exists, is unlike anything we know in our own solar system, and understanding what kind of world it would be, sitting out there in the dark, makes the hunt feel more concrete. Close your eyes and picture the outer solar system. Neptune is the farthest known planet, roughly 2.8 billion miles from the Sunday. The light that warms your skin took about 8 minutes to travel from the Sun to Earth. That same light takes about 4 hours to reach Neptune. Planet 9, if it exists, is somewhere between 15 and 40 times farther from the Sun than Neptune is. Light from the Sun would take between 2 and 3 days to reach it at its predicted average distance. By the time that light arrives, it is so faint it would be nearly invisible to the human eye, even if you were standing on the planet's surface. The Sun would appear as a very bright star, more brilliant than anything else in the sky, but still just a star. The temperature on Planet 9's surface sits around minus 370 degrees Fahrenheit. To compare, the coldest temperature ever recorded on Earth was around minus 130 degrees Fahrenheit in Antarctica. Planet 9 would be nearly 3 times colder than that. At those temperatures, any gas that once surrounded the planet would long ago have frozen solid onto the ground. Planet 9, if it resembles our solar system's ice giants, probably has a thick atmosphere of hydrogen and helium, with a mantle of icy material made of water, methane, and ammonia underneath. But with virtually no heat from the Sun, those materials would behave differently than on Uranus or Neptune. The planet is predicted to be somewhere between 5 and 10 times the mass of Earth. That makes it smaller than Neptune, but much larger than Earth. In our own solar system, there is a gap between Earth, the largest rocky planet at roughly 1 Earth mass, and Neptune, the smallest ice giant at about 17 Earth masses. Planet 9 would fill that gap. Astronomers actually call objects in this mass range super-Earths or mini-Neptunes, and they are remarkably common around other stars. Here is the irony. The type of planet Planet 9 is predicted to be is the single most common type of planet discovered in the galaxy. Our own solar system appears to be missing one. Every other planetary system astronomers have surveyed seems to have one of these mid-sized worlds. We do not, or rather, we might have one, but it got kicked to the outermost edge and sits there invisible. In the dark, in the cold, too faint to reflect enough sunlight to stand out against the background stars, moving so slowly that detecting its motion requires years of observation. If it is real, Planet 9 is a world hiding in plain sight, obscured by distance and temperature and time. And it has been out there, potentially since the beginning, circling the Sun on a path so long that by the time it completes one lap, civilizations rise and fall on Earth many times over. Where did it come from? This is where the story turns. Because the origin of Planet 9 forces us to rethink the entire early history of our solar system. It asks whether the arrangement of 8 familiar planets is the original design, or whether something enormous was removed from the picture long ago and shoved to the outer edge where we forgot to look. The answer to that question is one of the most surprising parts of this whole story, because Planet 9 may be in exile. A single year on Planet 9 would last between 10,000 and 20,000 Earth years. Sit with that. Human civilization, from the first cities in Mesopotamia to this moment, covers roughly 10,000 years. Planet 9 completes one orbit in the same span of time. It has been lapping the Sun since before your oldest ancestor who built anything left a record. And in that vast, slow orbit, the planet spends almost all of its time far from the Sun, deep in the cold outer solar system. Its orbit is not circular. It is a long, stretched oval. The planet swings in to its closest approach, then arcs back out to distances almost inconceivable. At its farthest point from the Sun, Planet 9 would be somewhere between 600 and 1,200 times the Earth-Sun distance away. To compare, our closest neighboring star system, Alpha Centauri, sits about 270,000 times the Earth-Sun distance away. Planet 9 is still well inside our own solar system at its farthest point, but it is so far out that the gap between it and the known planets feels like a different universe. That extreme orbit means Planet 9 spends the vast majority of its time in the place where it is hardest to find. At its farthest, it would be far too faint for almost any telescope we currently operate to detect. Its reflected sunlight, already barely a trickle, even at its closest approach, becomes essentially invisible at maximum distance. This is why we have not found it despite years of searching. Right now, at this exact moment, Planet 9 could be near the far end of its orbit. It could be sitting at maximum distance, as dark and cold as anything in the solar system, and it would look, to any telescope we currently point in its direction, like nothing at all. Brown and Batygin estimate that the planet is probably closer to us than the middle of its orbit right now. The reasoning is statistical. Objects in elongated orbits spend more time near the far end simply because they move slower there. But several lines of orbital evidence suggest Planet 9 is currently in the inner half of its orbit, still extraordinarily far, but within the range of detection for the most powerful telescopes. More importantly, it is within the detection range of a new telescope that changed the search entirely. A machine that photographs the entire southern sky every few nights, captures the faint movement of distant objects across multiple images, and processes tens of millions of alerts per week automatically. That telescope began its formal survey this year. For a planet on a 20,000-year orbit, a few years of searching is nothing, but those few years happen to coincide with the most capable solar system survey instrument ever built, pointing directly at the predicted search zone. What is coming next in this story is where everything either confirms or falls apart. And before we get there, we need to understand where Planet 9 came from in the first place, because its origin story forces us to look at our entire solar system differently. The 8 planets we know, the tidy family portrait we have used for 200 years, may have started with a 9th member, one that got thrown out of the picture before anyone was watching. 4.5 billion years ago, the inner solar system was a war zone. The young sun sat at the center of a swirling disk of gas, rock, and ice. Planets were forming from that disk, clumping together, growing heavier, clearing their orbits. Jupiter was the first to fully form, and it grew enormous. It became the largest planet in the solar system before the others were even half built. And when Jupiter was done growing, it started throwing things. Jupiter's gravity, at its current mass, is powerful enough to fling objects across the solar system with very little warning. Smaller bodies that wandered too close got launched outward. Some escaped the solar system entirely. Some got deflected into distant, elongated orbits in the outer reaches of the sun's gravitational territory. This kind of flinging is well documented. Jupiter has been throwing comets and asteroids onto new paths for billions of years. Astronomers have watched it happen with modern telescopes, In 2009, a comet hit Jupiter and left a dark scar the size of the Pacific Ocean. Jupiter is the solar system's most powerful gravitational sling, and it has been using that power since the beginning. The leading origin story for Planet 9 involves this process. Taken one step further, computer simulations of the early solar system show that the giant planets, Jupiter, Saturn, Uranus, and Neptune, did not form in their current positions. They were once much closer together and much closer to the Sunday. As they grew and interacted, their gravity pushed and pulled on each other. Their orbits shifted. The whole giant planet family reorganized over millions of years. In those simulations, roughly 1 in 10 model solar systems produces a fifth giant planet that forms alongside the others, but gets ejected during this reorganization. Jupiter and Saturn interact with the smaller fifth planet like two powerful bullies. The fifth planet gets slung back and forth between them, losing energy each time, until one final close pass launches it outward. Some of those ejected planets escape the sun's gravity entirely and drift off into interstellar space, but some end up in very distant orbits, still loosely bound to the sun, completing one full circuit every 10,000 to 20,000 years. That description matches Planet 9's predicted orbit exactly. If this origin story is correct, Planet 9 has been in its current distant orbit since the solar system was only a few 100 million years old. It was born near Jupiter and Saturn, grew alongside them, then got thrown out before Earth had developed its first ocean. It has been circling in the dark ever since. The exile story has a strange comfort to it. Planet 9, if it exists, belonged here. It formed from the same material as the rest of the solar system. It has as much claim to being a true member of this family as Jupiter or Saturn. It was just unlucky enough to cross paths with the two heaviest members at the wrong moment. But the exile story is not the only one that fits, because the sun did not form alone, and what happened in the first few million years of the solar system's life, before the nursery dispersed and the sibling stars drifted away, left marks we are still reading today. Stars are born in crowds. Our sun did not appear in an empty patch of space. It formed inside a stellar nursery, a dense cloud of gas and dust that was collapsing in multiple places at once, producing dozens or hundreds of stars in close proximity. For the first few million years of the sun's life, it would have been surrounded by sibling stars close enough to interact gravitationally. Most of those siblings had their own planets. And here is the strange thing about planetary systems being born in crowded nurseries. Gravitational encounters between nearby stars can transfer planets from one system to another. A rogue planet, one that has already been ejected from its parent star by the same kind of giant planet reorganization described in the previous chapter, floats between stars. If it drifts into the gravitational territory of another star, it can get captured. The new star's gravity pulls the wandering planet into an orbit. Computer simulations have modeled this process in stellar nurseries, and the results are striking. The probability that our sun captured a free-floating planet from a nearby sibling star during its first few million years is comparable to the probability of having produced the ejected planet scenario we already discussed. Both paths lead to the same outcome: a distant, massive planet in a very elongated orbit. The captured planet scenario adds one extra element. A planet that formed around a different star would carry different chemistry. It would have different ratios of elements, different interior structure, different atmospheric composition than a planet that formed from our sun's own disk. If astronomers ever land a probe on Planet 9 or analyze its spectrum remotely, they might find elemental fingerprints that match a different stellar birth environment. An alien world by origin, gravitationally adopted. Think about what that means for a moment. If Planet 9 was born around a different star, it spent its earliest life orbiting a different sun, different light, different heat, different gravitational rhythm, then it was flung free. It drifted through interstellar darkness for some period of time before drifting into our solar system's outer halo and getting captured. It carries in its chemistry the memory of a sun we have never seen and cannot name. The nursery scenario is also consistent with Sedna's existence. Sedna's extreme orbit, too far for Neptune to have caused it, too close for the classical Oort cloud to explain it, fits naturally in a model where the young sun's sibling stars were stirring up the outer solar system at close range before they dispersed. Sedna may be a relic of that stirring, and Planet 9, in this model, might be a captured immigrant from one of those departed siblings. The sun's birth cluster dissolved billions of years ago. The sibling stars are now scattered across the galaxy, thousands of light years away. We cannot trace which one donated a planet. We cannot verify the exchange happened, but the physics allows it. And an object in Planet 9's predicted orbit would fit a captured planet just as well as an ejected one. Which brings us to the third possibility, the wildest of the three. What if Planet 9 did not come from a sibling star at all, but from somewhere much farther away, from the vast dark between stellar systems entirely? The galaxy is full of homeless planets. Astronomers call them rogue planets or free-floating planets. They are worlds that formed around a star and then got ejected during the chaotic early period of their planetary system's life. They drift between the stars with no sun to orbit, warmed only by the residual heat of their own formation, gradually cooling in the dark over billions of years. Estimates suggest there are more rogue planets than stars in the Milky Way. Some models predict hundreds of billions of them, scattered across the galaxy in the vast empty spaces between stellar systems. If one of these wanderers drifted close enough to our Sun at any point in the last 4.5 billion years, our Sun's gravity could have pulled it into orbit. The probability of capture depends on the rogue planet's speed and trajectory as it passed. For the Sun to capture a planet, that planet has to pass through the right region of space at a speed that is slow enough for the Sun's gravity to pull it into a bound orbit rather than letting it fly straight through and keep going. That is a tight set of conditions. But the universe has had 4.5 billion years to run that lottery. A captured interstellar planet would arrive in a very elongated orbit, typically tilted at a steep angle relative to the existing planetary plane. Batygin and Brown's predicted orbit for Planet 9 has both of those properties, very elongated and tilted relative to the main planetary disk. What is also compelling is the timing question. The Sun's gravity extends much farther than most people realize. The Sun's gravitational territory, the region where its pull dominates, reaches far beyond the planets and out into a vast sphere called the Oort cloud. Any rogue planet passing through that outer territory, even thousands of times farther out than Neptune, would feel the Sun's pull. The probability of the Sun capturing a rogue planet is low per unit of time, but over billions of years, spread across the enormous outer halo of the Sun's gravitational reach, the probability becomes workable. Astronomers in recent years have observed 2 confirmed interstellar objects passing through our solar system. The first, named Oumuamua, arrived in 2017. The second, Borisov, arrived in 2019. Both came from interstellar space, traveled through the inner solar system, and left. Neither was captured, but their existence confirmed that interstellar objects do pass through our solar system with real frequency. If the right interstellar object, at the right speed, came through the outer solar system rather than the inner region, capture becomes possible. Planet 9 could be a visitor from the galaxy that arrived billions of years ago and has been slowly circling ever since, carrying no memory of where it came from, bound now to a star that was not its parent. The 3 origin stories, exile, adoption, and interstellar capture, all produce the same prediction for Planet 9's observable properties: a large, cold, dark world on a very elongated orbit tilted off the planetary plane. Orbital mechanics cannot distinguish between them. Only a probe or a detailed chemical analysis of the planet's atmosphere, if we could get one, might eventually tell us which story is true. The mystery of its origin may never be fully solved, but what we do know about Planet 9's current situation is deeply strange in its own right. Even setting aside where it came from, the question of why nobody has found it yet has a surprisingly simple answer. Sunlight does not reach Planet 9. Let that picture form properly. Hold up your hand and feel the warmth from a lamp or a window. That warmth travels from the Sun to Earth in about 8 minutes, crossing 93 million miles. By the time it reaches Neptune, the farthest known planet, the same light has traveled for about 4 hours and is already barely a fraction of what hits Earth. Planet 9 sits somewhere between 15 and 40 times farther from the Sun than Neptune. At that distance, the amount of sunlight arriving is roughly 1/10,000th of what Neptune receives, which is already dim. Neptune itself appears in the night sky only with a telescope. Planet 9, at its predicted distance, is darker than anything in our catalogues by a wide margin. Planets shine because they reflect sunlight. The more sunlight arrives, the more gets reflected back toward us. Take away the sunlight, and the planet effectively disappears. Planet 9 is so far from the Sun that it has almost nothing to reflect. The numbers are stark. From Earth, with our most powerful ground-based telescopes, Planet 9 would appear as a faint smudge moving against the background stars, too faint to have been picked up in any sky survey conducted before the last decade. The kind of faint where you need to combine multiple long exposures across multiple nights just to see it at all. It also moves slowly, very slowly. From our perspective on Earth, a planet's apparent motion across the sky depends on its distance. Close planets like Mars can cross the width of the full moon in a night. Neptune, the farthest known planet, takes about 165 Earth years to complete one orbit and moves very slowly against the background stars. Planet 9, 10 to 40 times farther than Neptune, moves even more slowly. Its motion against the background stars would amount to only a fraction of a degree per year. To detect something that faint, moving that slowly, you need to compare images taken months or even years apart. You have to see a very faint dot shift by a tiny amount against thousands of background stars. And you have to be looking in the right patch of sky. Here is the key problem. The sky is enormous. The region where Planet 9 might currently be located covers a large fraction of the southern sky. Searching for a slowly drifting smudge across that entire area, with the depth needed to actually see Planet 9, would take years with any single telescope. This is exactly why Planet 9 has not been found despite years of active hunting. Every team that has searched has covered only a portion of the possible search area, with the depth needed to detect the planet. Until now, because this year a new machine started scanning. It covers the entire southern sky every few nights. It goes deep. It sends out millions of alerts automatically. And its inventors specifically designed it to find things like Planet 9. But before we get to that telescope, there is a twist in this story that almost nobody saw coming. A pair of physicists who looked at all the same evidence and asked a completely different question. What if there is no planet at all? Two physicists walked into a planetarium in Chicago and came out with one of the strangest ideas in modern astronomy. Jakob Schultz and James Unwin were not astronomers. Schultz worked in particle physics. Unwin was a theoretical physicist. They had no particular expertise in the outer solar system. But after watching a short documentary about Planet 9 at the Chicago Planetarium, Unwin went home thinking about a question nobody had formally posed in the scientific literature. What if the thing bending all those distant orbits is not a planet? What if it is a primordial black hole? A primordial black hole is not a black hole that formed when a star collapsed. Stars collapse into black holes only when they are massive enough, and those black holes tend to be at least a few times the mass of our Sunday. Primordial black holes are different. They formed in the very first moments after the Big Bang, when the universe was dense and hot and collapsing pockets of matter could compress directly into black holes without going through the star stage. A primordial black hole with a mass 10 times that of Earth would be roughly the size of a bowling ball, maybe smaller. It would have an intense gravitational field concentrated in that tiny volume. It would exert the same gravitational force as any other object with 10 Earth masses, and it would be essentially invisible. Schultz and Unwin ran the numbers. A primordial black hole with the mass predicted for Planet 9 in the orbital position predicted for Planet 9 would produce exactly the same gravitational effects on the outer solar system: the orbital clustering, the tilts, the perpendicular objects, the sun's 6-degree lean. A bowling ball-sized black hole would mimic a planet gravitationally. You cannot tell them apart from the outside using orbital mechanics alone. That last point is the most unsettling part of the idea. Every piece of evidence assembled over 10 years of Planet 9 research, all the clustering data, all the tilt measurements, all the perpendicular orbits, all the centaur population patterns, would look identical whether the cause was a planet or a black hole. The gravitational signatures are indistinguishable. The only difference is what you see when you look directly at the source. Their paper, published in 2019, pointed to a separate line of evidence: an excess of faint microlensing events detected by the Optical Gravitational Lensing Experiment Survey. Microlensing happens when a massive object passes in front of a distant star, bending the star's light and making it temporarily brighter. The survey had detected more of these events than expected, with masses in the same range as Planet 9. The researchers suggested these could be primordial black holes drifting through the galaxy. If primordial black holes in that mass range exist and are more common than expected, one of them might have been captured by our solar system long ago. A bowling ball black hole circling the Sun in the same orbit predicted for Planet 9, doing the same gravitational work. The idea was widely regarded as unlikely by the planetary science community. Most researchers think an undiscovered planet is a far more probable explanation, but the paper raised a serious methodological point. All searches for Planet 9 have looked for reflected sunlight. A primordial black hole reflects nothing. It emits no light. Standard optical telescopes would never find it. If it is a black hole, the search strategy has to change entirely. A bowling ball-sized black hole drifting through our outer solar system would be undetectable by every telescope currently pointed at the sky. It emits no light. It reflects no sunlight. It produces no heat signature visible to infrared telescopes. It simply sits there, bending space, pulling on nearby objects, and offering no visual signal whatsoever. But there is one possible way to find it. Primordial black holes are thought to be surrounded by a halo of dark matter. Dark matter is a form of matter that does not interact with light at all. It cannot be seen, photographed, or detected by traditional instruments. But when dark matter particles collide with each other, under the right conditions, they annihilate. And when they annihilate, they release energy in the form of gamma rays. Gamma rays are extremely high energy forms of light, more energetic than visible light or X-rays. They pass through almost everything, and they travel in straight lines from wherever they are produced. A primordial black hole traveling through space would accumulate a dense halo of dark matter around it over billions of years. Inside that halo, dark matter particles collide constantly, producing a steady stream of gamma rays. A black hole in the predicted location of Planet 9 would appear to high-energy space telescopes as a faint, moving source of gamma radiation. Faint, moving, coming from the direction of the outer solar system. The signal would not look like a planet. It would look like a slowly drifting X-ray and gamma ray source, with no optical counterpart, no visible light, no infrared glow. Just high-energy radiation tracing the path of something invisible. Schultz and Unwin proposed that if all optical searches for Planet 9 came up empty over the next few years, the next step should be to search for this kind of gamma ray signal. An X-ray or gamma ray telescope could scan the predicted search region for moving high-energy sources. No one has conducted that dedicated search yet. This remains a long-shot alternative. The majority of astronomers working on the Planet 9 problem believe it is almost certainly a planet rather than a black hole. The primordial black hole hypothesis is considered theoretically possible but remains speculative. Microlensing data alone does not confirm primordial black holes in this mass range exist in the numbers needed to make capture likely. But the methodological lesson stands. If we only search using optical and infrared tools and the object is a black hole, we will never find it. Years of sophisticated sky surveys would return empty results. The absence of a detection would not tell us the outer solar system is empty. It would only tell us there is no planet there. The distinction matters. Two different objects in the same location producing the same orbital effects, requiring two completely different detection methods. One wrong choice of instrument, and you spend years searching empty sky for something you will never see that way. Before any telescope can get the right answer, scientists had to reckon with an even more fundamental challenge. What if there is no single object out there at all? What if the gravitational signal everyone has been chasing comes from something spread across billions of miles, with no single center, no single address, and no single telescope pointing that would ever catch it? Some astronomers looked at the same orbital evidence that led Brown and Batygin to predict Planet 9 and arrived at a completely different conclusion. No single hidden planet, a diffuse ring of small bodies instead. The idea is called the scattered disk hypothesis for the outer solar system's influence. The argument goes like this. Billions of years of interaction between the known planets, passing stars, and the galactic tide, meaning the slow gravitational pull of the Milky Way itself on the outer solar system, could have collectively sculpted the orbits of the extreme distant objects without any single massive body doing the work. Catherine Volk and Renu Malhotra proposed a related variation. Instead of a concentrated planet, a large population of small icy objects in the outer solar system, collectively massive but individually invisible to current telescopes, could produce some of the orbital clustering effects. Each individual object contributes a tiny amount of gravitational influence. Add enough of them together, and the combined effect mimics what a planet would do. Think of it like the difference between one large speaker producing a bass note versus hundreds of small speakers all vibrating at the same frequency. Either way, you hear the sound. Either way, the dishes on the shelf rattle. But the source is completely different. The scattered disk model has appeal. It avoids requiring an object we cannot find. It explains the orbital patterns using material we know exists in the outer solar system, just in greater quantities than we can currently measure. But it runs into serious problems. The perpendicular objects, those bodies orbiting at 90 degrees to the planetary plane, are very difficult to produce with a diffuse disk of material. A diffuse ring pulling gently from all directions tends to average out its effects. Pumping objects to extreme 90-degree inclinations requires a concentrated, massive body with a tilted orbit to drive the Kozai-Lidov mechanism described in an earlier chapter. The Sun's 6-degree lean is also hard to explain with a diffuse ring. A ring distributed symmetrically would not produce a net torque on the Sun's spin axis. You need an off-center, tilted mass to generate the torque needed. The Centaur population pattern faces the same difficulty. A gradual, smooth feeding of objects into the inner solar system from extreme distances does not naturally emerge from a diffuse ring. It requires a gravitational source with a specific mass and location. Every time astronomers tried to replace Planet 9 with a diffuse alternative in their simulations, one or more of the observed phenomena refused to fit. The diffuse disk model is a real scientific proposal and deserves serious investigation, but as of now, it does not explain the full set of observations as cleanly as a single massive planet does. When you need one explanation to account for clustering, tilts, perpendicular orbits, a tipped sun, and Centaur distributions all at once, a single concentrated source of gravity consistently outperforms a diffuse ring in every simulation run. The debate is alive, and it keeps the scientific community from becoming overconfident, because the outer solar system is still largely unmapped territory. The rules we are using to interpret it were written with very limited data, based on a few dozen distant objects out of what could be millions waiting to be found. and some researchers think the problem might go even deeper than missing planets or missing mass. What if the issue is with the rules themselves? Gravity is the oldest and best tested force in physics. Newton described it in 1687. Einstein gave it a deeper explanation in 1915. Between them, they have produced a framework that predicts the motion of planets, the bending of light around galaxies, the ripples in space-time detected from merging black holes. Gravity, as we understand it, has passed every test ever designed, but it has not been tested very thoroughly at extremely low accelerations over very large distances. The outer solar system is exactly that regime. Objects there experience gravitational forces billions of times weaker than what holds you to the ground. The accelerations are tiny, and some physicists have proposed that at those tiny accelerations, gravity might behave differently than Newton's and Einstein's laws predict. The framework is called modified Newtonian dynamics. It was originally developed in the 1980s by physicist Mordechai Milgram to explain something else entirely: why the outer edges of galaxies rotate faster than they should. In standard gravity, the outer stars of a galaxy should orbit more slowly, like the outer planets of the solar system orbit more slowly than the inner ones. But galaxies do not behave that way. Their outer stars move at roughly the same speed as the inner stars, as if there is more mass than we can see. Most physicists explain this with dark matter, an invisible form of mass filling the galaxy. Milgram's alternative was to change the gravity law itself at very low accelerations. When the acceleration falls below a specific threshold, he proposed, gravity strengthens slightly beyond what the standard formula predicts. A useful comparison: imagine Newton's law of gravity as a car engine that works fine in city traffic, but starts behaving unexpectedly on a long, nearly flat highway where you barely touch the gas. The car still moves, but differently than expected. In the outer solar system, the gravitational acceleration experienced by distant objects falls into the regime where modified gravity theories predict slightly different behavior from standard gravity. A handful of researchers have proposed that the orbital clustering effects attributed to Planet 9 could potentially be explained by modified gravity instead. The problem is that modified gravity theories, while good at explaining galactic rotation, are generally poor at explaining solar system phenomena. The specific type of clustering seen in the extreme trans-Neptunian objects requires a directional influence, something pushing in a specific direction from a specific location. Modified gravity changes the strength of gravity everywhere, not the direction. It produces effects that look the same in all directions. The clustering is not like that. It has a specific pointing direction in the sky. Most planetary scientists dismiss modified gravity as an explanation for Planet 9's effects. The mismatch between what modified gravity produces and what the observations show is significant. But the alternative exists, is taken seriously by some physicists, and serves as a reminder that every extraordinary claim demands careful examination of even the most fundamental assumptions. Before you claim a new planet, you have to rule out the possibility that the rules you use to predict it have a hidden flaw. The outer solar system is testing those assumptions every time a new, distant object is found and its orbit mapped. And the results keep coming out stranger than the equations written 2 centuries ago predicted. 4 billion years ago, a star may have passed through the outer solar system. The sun's neighborhood in the Milky Way is not empty. Stars move, slowly by human standards, but relentlessly over geological timescales. Every few million years, a star passes within a few light years of our Sunday. Rarely, a star gets close enough to have measurable gravitational effects on our outer solar system. A close enough stellar passage, meaning a star coming within a few hundred times the Earth-Sun distance, would do something remarkable. It would gravitationally scatter the objects in the outer solar system, changing their orbits, pulling some onto extreme paths, pushing others out entirely. The effects would persist for billions of years after the star was long gone. Picture dropping a boulder into a pond and then quickly pulling it back out. The ripples continue spreading long after the boulder is gone. You would see the ripple pattern in the water and know something large had been there. even if the boulder was nowhere in sight. The outer solar system may be showing us the same kind of ripple, the orbital pattern left by a star that passed through and kept moving. Sedna's orbit has been one of the strongest arguments for this kind of event. The closest Sedna gets to the Sun is already so far that Neptune's gravity barely touches it. Something with a larger, temporary gravitational presence would have been needed to push Sedna into its current path. A passing star in the early solar system is a plausible candidate. Some researchers have proposed that the same stellar passage that produced Sedna's extreme orbit could also have created the clustering signature that Brown and Batygin interpret as Planet Nine's influence. A massive star sweeping through the outer solar system at close range would gravitationally herd distant objects as it passed, nudging them into aligned orbits in the direction the star came from. The star would then move away. The alignment would persist. And millions of years later, astronomers looking at those clustered orbits might mistake the gravitational memory of a departed visitor for the ongoing influence of a hidden planet. The passing star hypothesis has real problems. Computer simulations of specific close stellar encounters show that the clustering produced does not match the observed pattern as well as a bound planet does. A passing star sweeps through, disturbs things, and leaves. A bound planet continues to interact, dynamically herding and maintaining the clustering over billions of years. The long-term stability of the observed clustering favors an object that is still present, but the passing star model remains in the scientific conversation, and it points to something important. The outer solar system carries the memory of every gravitational event in the Sun's 4.5 billion year history. Sedna is a fossil. The clustering may be a fossil. Even the Kuiper Cliff may be a fossil of Neptune's early migration. Everything out there was shaped by something. Every orbit carries a memory of a force that acted on it billions of years ago. And sorting out which shape belongs to which cause is the central challenge of this field right now. One astronomer has argued more loudly than most that this sorting process is not going as well as the Planet Nine supporters believe. Samantha Lawler does not think Planet Nine exists. Lawler is an astronomer at the University of Regina, and she has spent years studying the outer solar system and the statistics of how we observe it. Her argument is precise and serious. The orbital clustering that Batygin and Brown interpret as evidence for Planet Nine may be an artifact of how and where we look, not a real feature of the outer solar system. Telescopes do not scan the sky evenly. They observe patches where conditions are best. Low on the horizon is harder. Areas near the Milky Way are harder because background stars overwhelm faint moving objects, and time on major telescopes is limited and allocated based on specific science goals. The result is that discoveries of distant outer solar system objects are heavily biased towards specific regions of the sky. Lawler's concern is this: if you discover most of your extreme trans-Neptunian objects in the same general patch of sky, because that is where your telescopes are mostly pointed, the orbital elements of those objects will naturally cluster in ways that reflect where you were looking, not where the objects actually concentrate in the real solar system. A simple analogy makes this concrete. Imagine someone counting cars in a city and spending 90% of their time on one highway. Their data would show that most cars use that highway. The bias in the counting process creates a pattern that was never in the real world. Lawler argued this is exactly what happened with the early Planet Nine evidence. The discovery teams spent much of their observing time in the same region of the sky. The orbital elements of their discoveries reflected that, not some underlying gravitational influence from a hidden planet. In 2020, two major surveys published findings that cut against the clustering evidence. The Outer Solar System Origins Survey documented over 800 trans-Neptunian objects while carefully tracking which parts of the sky were observed and which were not. When the team adjusted their statistics for observational bias, the remaining clustering signal weakened considerably. A separate survey from the Dark Energy Survey, analyzing 316 new objects, reached a similar conclusion. Lawler said directly that the Planet Nine hypothesis, as originally proposed by Brown and Batygin, does not hold up to detailed observations when you account for observational bias in a large sample. Brown and Batygin pushed back. They argued that the samples used in those surveys do not extend to the most extreme distances where Planet Nine's influence would be strongest. The closest objects in any outer solar system survey are not the ones Planet Nine would gravitationally sculpt most clearly. Only the most distant extreme trans-Neptunian objects carry the clearest signal. Both sides have real points. The debate is not resolved, and Lawler's warning matters regardless of where the ultimate answer falls. Even if Planet Nine is real, confirming it requires data that is clean enough to distinguish gravitational clustering from observational selection effects. The only way to settle it is more data, much more data, covering the full sky, down to the faintest possible objects, with careful records of exactly where and how long each region was observed. That is the exact specification for the telescope that just came online. In 2023, the Subaru telescope, on top of a volcano in Hawaii, found something frozen and ancient at the edge of the solar system. The object was small, somewhere between 140 and 240 miles across, roughly the width of Colorado. It was dark red, the kind of deep reddish color that comes from billions of years of cosmic radiation, baking the organic compounds on an icy surface. It moved slowly against the background stars, and its orbit placed it in a region of space where only 3 other known objects had ever been found. Scientists gave it the official name 2023 KQ-14. They nicknamed it Ammonite, after the spiral-shelled fossils found in ancient rock. The name was chosen because objects like this are expected to be frozen records of the solar system's earliest history, preserved in the deep cold far from the sun's heat. Ammonite belongs to a class of objects called sednoids, named after Sedna. Sednoids are extreme objects whose closest approach to the sun sits so far out that Neptune's gravity barely touches them. They exist in a gravitational no-man's land, too far for the planets to have sent them there recently, too close to have arrived from the far outer Oort cloud. Only 4 sednoids have ever been confirmed. Sedna was the first, discovered in 2003. Now Ammonite was the 4th. Its discovery was expected to be exciting news for Planet Nine researchers. More sednoids meant more potential evidence of the hidden world's gravitational influence. Then the orbital data came in, and the mood shifted. The 3 previously known sednoids all have a property that loosely supports the Planet Nine hypothesis. Their orbits, while not perfectly aligned, can be loosely grouped in a general direction. Astronomers have cited this grouping as one thread of the overall clustering evidence. Ammonite's orbit points the other way. Its orbital orientation is misaligned from the other 3 sednoids. Instead of adding to the grouping, it breaks it. The direction Ammonite's orbit points does not match the direction a Planet Nine in the predicted location would tend to produce. This was not a small discrepancy. The misalignment was clear. Ammonite's perihelion direction sits well outside the region where Planet Nine's gravity would tend to shepherd objects over billions of years. If the planet is where the models say it is, Ammonite should not be pointing the way it points. Astronomer Yukun Huang stated plainly that Ammonite's current orbit, not aligning with those of the other 3 sednoids, lowers the likelihood of the Planet Nine hypothesis. The team proposed an alternative interpretation. Perhaps all 4 sednoids were on similar orbits 4.5 billion years ago, when the solar system was young and have slowly diverged over time through other processes. If that is the case, the current misalignment does not disprove Planet Nine. It just means the original alignment has been scrambled by billions of years of gravitational evolution. But there is a more unsettling possibility, Huang raised. A planet once existed in the solar system but was later ejected, causing the unusual orbits we see today. The orbits are the footprints. The sculptor has already left. The gallery remains open, but the artist is gone. Ammonite has been on its current path since the solar system was young. Scientists ran simulations of Ammonite's orbit backward through time. They traced where it would have been 1 billion years ago, 2 billion years ago. all the way back to 4.5 billion years ago. The orbit held, stable throughout, unchanged since the era when Earth's surface was still molten and the Moon had only just formed from the debris of a giant impact. That stability carries a specific message. Orbital stability at Ammonite's distance requires an absence of strong gravitational disruption over long timescales. If a large planet were currently circling the Sun at the distances most Planet 9 models predict, specifically within about 400 times the Earth-Sun distance, its gravity would gradually perturb Ammonite's orbit over billions of years. The orbit would shift. It would not look as clean and stable as it does. Picture a spinning top running on a smooth table. It spins steadily and stays upright. Now put a heavy book on one corner of the table. The table tilts slightly. The top wobbles. Over time, the wobble grows. The top eventually falls. Ammonite's orbit is the top that has not wobbled, suggesting nothing heavy has been sitting on the nearby table for a very long time. The team that discovered Ammonite ran those numbers carefully. Their conclusion: Ammonite's stable orbit is most consistent with a hypothetical planet sitting at significantly larger distances than the originally proposed models, somewhere around 500 times the Earth-Sun distance or beyond, rather than the closer range of 200 to 400 originally estimated. That is further out than most predictions place Planet 9. A planet at 500 or more times the Earth-Sun distance would be harder to detect. Its reflected sunlight would be even fainter. It would move even more slowly. It would be even more invisible to current telescopes. The Ammonite result does not disprove Planet 9. Multiple scientists on the Discovery team made that clear. But it reshapes the search. If Planet 9 is real and Ammonite's orbit is reliable evidence, the planet is probably lurking even farther out than Batygin and Brown first predicted. Or it may have been present long ago and left. The ejection scenario is haunting. A world that sculpted the outer solar system for billions of years and then got a final gravitational kick from some passing disturbance and escaped into interstellar space. The orbits we are observing would then be the aftermath, an ordered pattern left by a sculptor that has already wandered away into the dark between the stars. And it would not be coming back. A world that escapes the sun's gravity, at distances this large travels, with enough speed to keep going indefinitely. No orbit, no return path, just straight into the galaxy, carrying the chemical memory of a solar system it once belonged to. If that is the case, the pattern is real. The cause is gone, and no telescope will ever photograph it, because it is no longer here. But before anyone accepted that possibility as the final word, a pair of old satellites offered a different kind of clue. Photographs taken decades apart, sitting forgotten in archives, apparently showing a single faint dot in two different places in the sky. Two space telescopes, launched 23 years apart, each photographed the same tiny patch of infrared sky at different times. Neither telescope was looking for Planet 9. Neither was operational when the search began. But their archived data, sitting quietly in scientific databases, held something that researchers in 2025 decided to look for. The Infrared Astronomical Satellite launched in 1983. It was a joint mission between the United States, the Netherlands, and the United Kingdom. It mapped the entire infrared sky over the course of about 10 months before running out of coolant and going silent. The data it collected sat in archives for decades, occasionally reanalyzed by astronomers mining it for new discoveries. The second telescope, a Japanese infrared satellite launched in 2006, ran for about 18 months before its coolant also ran out. Same story. Rich archival data, largely untapped. The two missions together covered the infrared sky at different times with different instruments. Neither was designed with Planet 9 in mind. Neither was designed with each other in mind. They were simply two separate windows into the same universe, opened 23 years apart. A team led by a graduate student named Terry Long Fan at National Tsinghua University in Taiwan had an idea. If Planet 9 was in a known region of the sky and moving slowly, it should appear in both infrared datasets but in slightly different positions, because 23 years of orbital motion would have shifted it a tiny amount. By cross-matching the two datasets, filtering out known objects, and looking for a moving dot with the right brightness and color, they might find a candidate. They started with a catalogue of roughly 2 million objects in the two datasets combined. They applied filter after filter, known sources removed, objects that did not move over time removed, objects with too much noise removed, objects near bright regions of the galactic center removed. 13 candidate pairs remained. They checked each by eye. One survived, 2 dots, one in the 1983 data and one in the 2006 data. Same color, same brightness, positioned where an object with a Planet 9 mass and orbital distance would have drifted in 23 years. Fan described feeling very excited when the candidate pair appeared. An entire year's worth of careful filtering came down to 1 dot. He confirmed the brightness matched. He confirmed the color matched. He confirmed the spacing matched the expected motion. The team moved forward. They published their work. The candidate was real enough, they argued, to warrant follow-up observations with more powerful telescopes. Whether the dots were truly the same object or a coincidence of two unrelated sources in two unrelated datasets was something only new observations could resolve. Some astronomers reacted with interest. The possibility that Planet 9 had been sitting in archived data since 1983 was intriguing on its face. If true, it would mean the planet was photographed 40 years ago without anyone knowing. It would mean the answer had been available in a data tape in a storage room, waiting for the right question. Others were more cautious. Faint infrared signals in old datasets are tricky. Noise behaves in unexpected ways. Coincidental matches between sources in two surveys, taken 23 years apart, are more common than intuition suggests. The scientific community's response was divided. Some found it intriguing, and then Mike Brown ran the orbit himself. Mike Brown was not involved in the infrared study. He heard about the candidate through normal scientific channels and decided to run an independent calculation. He took the two positions of the candidate dot, separated by 23 years, and worked backward to determine what orbit would connect them. The math is standard. Give an astronomer the position of an object at 2 points in time and the gravitational properties of the Sun, and the orbital parameters follow from the physics. The process is the same one that led to Neptune's discovery in 1846. Take the position of something at one moment, then again later, and the math tells you where it has to be coming from and where it is going. For Neptune, the math said it was out there beyond Uranus. For this infrared candidate, Brown set up the same equations. The result stopped him cold. The orbit he calculated placed the object on a path tilted about 120 degrees from the plane of the solar system. To compare, Planet 9 is predicted to be tilted about 15 to 20 degrees. The candidate's tilt was more than 6 times larger, and that enormous tilt meant the object would be orbiting in the opposite direction from all the known planets, a retrograde orbit. Clockwise when viewed from above, when everything else in the solar system goes counterclockwise. An object like that would look strange. It would come from the opposite direction in the sky compared to known planets and most known small bodies. And its gravity would pull on the outer solar system from a completely different angle than Planet 9's predicted pull. It could not produce the clustering. It could not produce the tilts. It could not explain the perpendicular objects. Brown was direct when he assessed the result. He said the candidate would be tilted roughly 120 degrees from the solar system's plane and would therefore have none of the effects on the outer solar system that Planet 9 is predicted to produce. Whatever the infrared signal was, if it was real at all, it was not the planet he had been hunting for 10 years. This left the community in an uncomfortable position. The candidate might still be a real object, Something orbiting backwards at extreme distances with a tilt like that would be a discovery in its own right. It would demand its own explanation. But explaining it as Planet 9 requires the orbital mechanics to fit, and they do not. The candidate remains unconfirmed. Follow-up observations are needed to determine whether the two infrared dots are actually the same object moving over time, or a coincidence of two unrelated sources appearing in similar positions in two different datasets. Until a third detection pins down the orbit independently, the candidate sits in the uncertain middle ground between discovery and artifact. Science is full of that middle ground, signals that look real from one angle and dissolve from another, candidates that survive months of analysis and fail a single independent check. The infrared candidate is in that territory right now. It is real enough to publish and uncertain enough to hold back any celebration. And while that particular lead cooled, the machine that will settle this once and for all quietly began its work on a mountaintop in Chile. On a mountain called Cerro Pajón in the Chilean Andes, at an altitude of about 8,800 feet, a telescope unlike any built before it has been scanning the southern sky. The Vera C. Rubin Observatory is named after Vera Rubin, the astronomer who spent decades gathering evidence for dark matter by studying how galaxies rotate. Her work transformed our understanding of the universe. The observatory bearing her name is set to do the same for the solar system. The camera on this telescope contains 3.2 billion pixels. It is the largest digital camera ever built for scientific research. Its field of view is so wide that it can photograph an area of the sky 40 times larger than the full moon in a single exposure. Every few nights, it photographs the entire visible southern sky, and then it does it again and again and again for 10 straight years. The scale of data this produces is almost hard to picture. Every night, the telescope generates between 10 and 20 terabytes of raw information. 1 terabyte is roughly 200 full-length movies. The telescope produces that much data every single night, automatically, and the system processes it within seconds of each exposure. Astronomers designed it specifically so that alerts about moving or changing objects get issued in real time, not weeks later. Each time it photographs the same region it photographed before, automated software compares the new image to the old one. Anything that has moved, brightened, or dimmed triggers an alert. During a single night of test observations in early 2026, the observatory generated over 800,000 alerts. When full operations ramp up, the number is expected to reach several million per night. Searching for Planet 9 in that data involves looking for an extremely faint dot that shifts position between observations separated by weeks or months. The shift would be tiny. The dot would be close to the edge of detectability, but the camera is deep enough, wide enough, and the survey cadence is frequent enough that if Planet 9 is within the predicted search zone and brighter than a certain minimum, the system will flag it. Scott Shepard of the Carnegie Institution for Science estimated that if Planet 9 is real and within the original predicted range, the Rubin Observatory has roughly a 70 to 80% chance of finding it within the survey's first few years. 70 to 80% is not certain. If the planet is at the extreme far end of its orbit right now, as Ammonite's stability data suggests it might be, it would be fainter and harder to detect even for Rubin. If the planet is smaller or darker than predicted, it could sit right at the edge of Rubin's detection capability, possibly requiring 2 or 3 years of data stacked together to pull a signal out of the noise. But within the first year or two of full operations, Rubin should either find a candidate or significantly constrain where Planet 9 can and cannot be. Astronomers will know more by the end of this year than in the previous decade of searching combined. The data will not wait. The trap is set. The bait is the outer solar system itself. The machine is watching. The next few years will change our understanding of where we live. Konstantin Batygin said it plainly in the summer of 2026. The new batch of outer solar system discoveries from the Rubin Observatory, coming in throughout this year and next, will be a direct test of every line of evidence that has been built up over 10 years of hunting. The clustering, the tilts, the perpendicular objects, the Centaur distributions, all of it will face the largest, cleanest dataset ever collected from the outer solar system. Two outcomes are possible, and both are extraordinary. The first outcome is that Rubin finds it, a faint dot, moving slowly against the background stars, reappearing night after night in the same position, shifting slightly month after month. Orbital calculations confirm the distance, the mass, the elongated path. The predictions match. Planet 9 is real. If that happens, the solar system gains its ninth member back. The chair that was emptied by vote in 2006 gets filled by discovery. We would know for the first time that our solar system harbors a world nearly invisible to us for its entire history, circling overhead for billions of years, while civilizations below had no idea it existed. We would know that the familiar 8-planet map we have used for 2 decades was always a picture with something missing, and depending on the orbit's properties, scientists would begin unraveling its origin story. Was it born here and exiled? Was it stolen from a sibling star? Did it drift in from interstellar space? The orbit itself carries fingerprints of its history. The second outcome is that Rubin finds nothing. If Rubin surveys the predicted search zone to the required depth over 2 to 3 years and finds no planet, the hypothesis is in serious trouble. With Rubin's capabilities, a sufficiently bright and close enough Planet 9 should appear. Its absence would push the community toward either accepting the planet is far more distant than predicted, or accepting that the clustering signal is an artifact. That result would be equally important. The pattern would need a new explanation. The outer solar system would remain mysterious, but differently so. Samantha Lawler's warning about observational bias would gain force. Ammonite's misaligned orbit would gain new significance. Every piece of evidence built up over 10 years would need to be re-examined through a different frame. Either way, we are about to find out what is hiding at the edge of our solar system. For most of human history, the solar system ended at Saturn, then it ended at Uranus, at Neptune, at Pluto. Every time we looked harder, it turned out to be bigger, stranger, and more crowded than we had assumed. The search for Planet 9 is the same story continuing. Something out there has been bending the orbits of distant worlds, tilting them, clustering them, pushing them sideways, leaving its mark on the sun itself. We know something acted on this solar system from the outside, from the far edge, from a place where sunlight barely reaches. We just have not put a face to it yet. The search for that face has consumed careers, challenged textbooks, divided the scientific community for 10 years, and produced more questions than any single decade in the history of solar system science. The answer is a few nights of data away.